Well, welcome to the Middlesex Moments radio show. I'm Dr. Anna Wasescha, president of Middlesex Community College, located right here in Middletown, Connecticut. And today my guest is my perennial guest, Steve Krevisky. He teaches mathematics here at Middlesex. He's done that for over 30 years now. And as you all know, those of you who are loyal fans of the Middlesex Moments radio show, he knows more about baseball than any other human being on the planet. Just for repetition's sake, because repetition is a good way to learn, I want to remind everybody that in the 2017 season, Steve was goaded by me, and he acquiesced, to project who might win the World Series this year. And the answer was, although it was hard to, nothing is sure, and there's no crystal ball, but the answer he gave us was the Cleveland Indians and the Washington Nationals would be in the World Series. So I just want to remind those listeners here today that they want to keep an eye on the World Series, which will probably be next October, maybe?
Or November.
Yeah, November even. Just to see if Steve was right about that. So he teaches everything related to statistics, mathematics, including statistics and probability. So, it's all related. But today, the subject of this radio program is the international mathematics community around the world. And Steve is a prodigious world traveler, and has gone to many, many conferences over the summers generally. And I thought I would ask him to tell us what he's learned by traveling the world and talking to other mathematicians and math educators. So, I don't know anything about math except that I think it's a foreign language, but also a universal language. So, how did you even get interested in going to these conferences around the world?
Well, thank you, Anna. Nice to be back again. Many years ago, going back to the 80s, I had a chance to go to this International Congress on Math Education in Budapest, Hungary, a place I've visited several times since then. I got to stay in somebody's house on the Pest side of the Danube, and the conference was held on the Buda, the older side, across the Danube at this technical institute. I'd started traveling back in the 80s when I lived in Wisconsin before I came here, and so when I saw a chance to go to an interesting conference in a faraway place, I decided that was the right time to do that. I had a couple of years before, in '86, I went to this international conference on teaching statistics way out in British Columbia in Victoria. And so then after that, I took the train across Canada. So it sort of started back in the mid to late 80s when I had a chance to combine work and travel, which I've done many times since. And what I remember also about the conference in Budapest was I got to live in someone's house for 8 days, eat breakfast there, and every day take the tram across the Danube and go to the conference and see the city. And we had an excursion to the Puszta, the plain, where we got to eat the Hungarian goulash, the thick stew that I've come to enjoy, and see people ride horses, one foot on one horse, the other foot on the other horse. So part of it was the cultural experience of being in another country and then seeing what my fellow mathematicians or statisticians do. And so what I have here with us today is different math books from other countries, including a book on math competitions in the Balkan countries, which I visited for a conference in 2010.
Let me just stop you there so we can take a break, and then when we come back, we'll talk about the books that he's laid out here on my table. So we'll be right back after this message. So welcome back to Middlesex Moments radio show. I'm Anna Wasescha, and today my guest is Steve Krevisky, who is a math professor here at Middlesex Community College and who's traveled the world meeting with other math educators. As we were breaking right before the break, he was talking about the cultural aspect of all of this. So I guess my big question, the overriding question is math education different country to country, or is it roughly the same?
It's a good question, Anna. We've been learning about best practices of other countries. The Asian countries do very well on these TIM studies, meaning Trends in International Mathematics and Science Studies. We've learned about like the Singapore bar method as a way that they teach fractions. I learned something about that when this International Congress on Math Education was in Korea in 2012 in Seoul. So we're learning about some of those best practices, and also through this discussion group on two-year colleges that we've had at those conferences, finding out about what do math professionals in other countries have in common with us in terms of stuff like underprepared students. We always talk about that. Need for professional development of the faculty. And it's interesting to see how, let's say, they might teach a particular topic. When I went to my National Two-Year Math Conference last November, there was a presentation about comparing math education in the U.S. versus Hong Kong and, let's say, teaching functions. And the problems that they did for the students in Hong Kong seemed to me to be more rigorous in terms of how students have to approach and think about a problem, and finding the equation of a parabola, let's say something like y equals x squared for our listeners out there. And so we're learning more about those kinds of best practices, and talking about what can we do in terms of global education, and maybe eventually sending students abroad or having students come here, things of that nature. So I think it's good for us to learn how other countries do things. The last Congress I went to, the International Congress on Math Education, or IGME for short, was in Germany last summer. And so I was just at a workshop last Friday where I found out that evidently in Germany some of the practices are similar to ours, although their higher ed structure is often very different. So I think it's good for us to learn about things like that. And I collect math books from other countries where the math is pretty much the same as what we do. It's just different describing language. Now, students from other countries might do a particular problem in a different way from what we do, but still end up with the same answer.
What about the difficulty of the mathematics combined with the year in school the student is? So I'm curious about Asia. Do they push students at a younger age to accelerate through various levels of math? Math is something, it's pretty linear, right? You have to know algebra in order to get to calculus. So did you get stories from Korea and Singapore and other places like that, Japan, where the students, let's say in elementary school, are doing what we expect students in high school to do?
Yeah, I have a sense that I think they do more homework than our students do, let's say, in elementary, junior high, and high school. And I think they get pushed more, and that Asian students can go to these after-school programs where they can work on math and maybe other subjects. And I know that in Europe that students specialize a lot sooner than our students do. So I think there are some structural differences in other countries along with how students might be pushed along to achieve.
There's another element to that. So it's the age at which you expect people to start doing higher level math. And I will say my experience in higher education, what we euphemistically refer to as whiz kids, the 11-year-olds who are freshmen in college, the area where they are whizzes is almost always science and math, always. Even that was true even with Ted Kaczynski, who was the Unabomber. He went to Harvard when he was 14 or 15 years old, and mathematics was what his field was. So there's something about the human brain that is able to master really complex mathematics at a really early age. So there's that piece of it, the age at which you get to be able to do mathematics. But the other piece of it is the way we hold our classes in United States, which is a lot more interactive, right? So I get the sense that in Asia, maybe in Northern Europe, the teacher is the master of the room, right? They are the authority. And the students don't do much to challenge that. I mean, do people talk about that at these conferences?
We haven't gotten to talk enough about that kind of pedagogy. I would like to see that more, because here we talk about engaging and interacting students, and there's different ways of doing that, and changing curriculum and stuff like that. In Japan, you have the lesson study method, I witnessed that at a Japanese school down in Greenwich several years ago, where a teacher teaches a lesson and then other teachers might observe it, and then a different teacher might teach a similar lesson maybe a couple of days later. So I think there's some things that could be learned in terms of different pedagogies that speaks to what you're saying, that that you can have group work, you can have, like we're working on the open source materials, and in my case using the sports data in my math classes and things of that nature. There's a research basis for that. So I think other countries could do similar kinds of things. Now here, as a follow-up, a lot of our students typically might, let's say 9th grade Algebra 1, 10th grade Geometry, 11th grade Algebra 2, and then as a senior, if they're ready, Calculus or Pre-Calculus, and I think more students are doing stats in high school as well. So, but I think there's some things that could be done in terms of changing the pedagogy, changing the structure of when we offer certain things. There's also the question of use of the calculator. A lot of our students use the calculator, which I sometimes have a mixed bag about, because I've seen students who are lost without the calculator. In other countries, I don't know that they rely on it as much as we do. I think it's a good tool once students know the basics, because then they can do more complex problems with aid of the calculator. And now on our math contest that we just had a few weeks ago, we do allow calculators, but we still want our students to think.
Sure. Yeah, absolutely. So, when people work things out on a sheet of paper with a pencil, those are basic arithmetic skills to some degree, right? It's multiplication, division. Yeah.
Yeah, like when we talk about orders of operations, which comes up in all of our classes, some of our listeners might remember, please excuse my dear Aunt Sally, PEMDAS, parentheses, exponents, the whole scheme for orders of operations. That's something that comes up in all of our classes that students need to be able to do. And I often say to my students that I like to do things by hand so that then the students know why they're seeing what the calculator might tell them.
Sure, exactly.
And there's probably different opinions about that sort of thing.
Yeah, right. Well, though, I do tend to subscribe to the idea that you end up being more self-reliant if you sort of figure out that you aren't going to get a lot of help from someplace else. So you got to figure it out. So you have to tune your attention into the problem and sort it out as though you were on a desert island. There's nobody else there who can help you along the way. So I have another question about this, which is, what's your view about mathematics qua mathematics? I think you should just learn mathematics, do mathematics sort of in a vacuum, versus the move in this country toward contextualized mathematics. So you should learn math because it's a lot more than balancing your checkbook, but you could begin by balancing your checkbook. But then you would be able to make other decisions, because almost every decision we make in the end has got some numerical basis. We rely on data, so we interpret things that people tell us about what the most nutritional food is or what the most effective cleanser is, and it's all based on statistics. So that's contextual. And then there's kind of the pure math side. What was your experience in college? Were you in a pure math kind of environment?
Yeah, that's an excellent question, Anna, that I think sometimes there's, perhaps a debate of sorts between the pure math, doing math for its own sake, that a research mathematician may or may not be interested in an application to a problem, as opposed to applied math that fits what you're saying, using math to help consumers make better decisions, which fits what you're saying, or maybe statistics could help advance social justice type issues. So that's more the applied side of things. I don't think that they're in contradiction necessarily, but here at Middlesex, where we're interested in teaching and hopefully getting students to think, when we run the math contest, as I did a few weeks ago, then although the level of math isn't that high, there's a lot of out-of-the-box problems, and the calculator might not help the student if they don't know how to approach a problem and think.
Right. It's really reasoning. So we have to take another break. But when we come back, let's talk about math and its utility in our lives.
Mm-hmm.
Well, welcome back to Middlesex Moments Radio Show. My guest, Steve Krevisky, teaches mathematics here at Middlesex. And when we broke off right before the break, and we're breaking before the break, that I should find another way to say that. We were talking about, pure math versus the utility of math. Mm-hmm. So, what kind of experience did you have when you were in undergraduate school in mathematics?
Okay, well, I was at City College of New York as an undergrad. I'm from New York originally. So I went through a lot of the pure math stuff, and after the calculus sequence, then there was advanced calculus, and then you get into stuff like abstract algebra, number theory, topology, real variables, complex variables, etc. And that continued into grad school before there was a later change in direction to math education. So if you get into some of that stuff, it can seem kind of abstract. And so listeners might wonder, where would you use stuff like that? So if you're into more of the application type stuff, as I started to mention before, things that can help consumers, or later on in the 80s, I started to get into stuff with the baseball statistics or sabermetrics, which I do a lot today in my classes and beyond through like the Society for American Baseball Research, or SABR. So, you could do those kinds of things, or, you could use math in terms of, like, let's say if you're buying a car, decisions about things like that, or financing your house. So I think the question often does get asked, where would you use math?
Right.
So it might show up in surprising ways.
Yeah, but I have to say I am endlessly curious about your experience in graduate school in mathematics, because when you're taking topology or you're taking courses in real versus complex variables, there must be this is not my field. There must be mathematics problems that people are still trying to resolve, and then those things must in the end apply to very big questions, like, for example, the questions about outer space and the expansion of the universe and black holes and how they work. All that stuff has all physics has got a mathematics base. Yes. Just that I found out by taking physics in college. But so what are the things that mathematicians are trying to solve that are in the pure math area?
Well, one of the famous problems that was big news back in the 90s and 2000s was something called Fermats' last theorem. Pierre de Fermat was a mathematician back in the 1600s, and readers may be familiar with the Pythagorean theorem, like a squared plus b squared equals c squared in a right triangle, where all the exponents are 2. So Fermat's last theorem had to do with the matter of, if you change the exponent to, let's say, make it a to the third plus b to the third equals c to the third, can you find solutions with let's say with positive integers where none of a, b, and c are equal to 0? And so it turned out to be a more complex problem than people might have thought. And so this mathematician from Princeton, Andrew Wiles, was trying to solve this back in the 90s. And he thought he had a solution, and it turned out he found a mistake. And then he had to go back and fix it. And then he eventually did solve it. As Fermat supposedly wrote down a solution on the proverbial napkin. You may have heard of that sort of thing. But the proof was never found anywhere. And so Wiles was working on this problem for a long time. And it might seem kind of abstract, but he brought in different aspects of math, number theory, and elliptical geometry, and other kinds of things. So that was kind of a seemingly abstract problem that mathematicians can get very caught up in, as opposed to something of that might be more concrete for our students or for our listeners.
Sure. But what is the utility? It's almost an oxymoron, but what would be the utility of solving Fermat's theorem? How does that work?
I don't know if any practical applications have been found, but another area in math that might be more visual that listeners may have heard of is fractal geometry. Mandelbrot, back in the early 80s, worked on and discovered this area in terms of fractals that has to do with geometric shapes and how they can be reproduced. Like, let's say, if you think about taking a triangle and either blowing it up or shrinking it. And so that aspect of fractals, where geometric shapes get reproduced, led to a lot of beautiful designs that had implications for art and maybe architecture and other areas. So that aspect of fractals did result in something that might seem more practical, and that perhaps our colleagues in the art department might be able to comment on that, because I talked to them about the relationship between math and art. Mm-hmm. So that might seem more practical, so that in terms of thinking about how would you engage students, get them thinking about things beyond, the routine stuff that they might otherwise do, that was another area. And again, for me, the baseball stats or projecting the NCAA basketball tournament, which is an ultimate exercise in probability.
Mm-hmm. Right.
So
right.
I do a lot of stuff like that.
So there must be a community, to go back to this international element of the mathematics profession, there must be a community of people internationally who are working on mathematics problems. And it must be easier to share now because of the internet.
Well, yes, with this book on the table here, the Balkan Mathematical Olympiads, I got that at that ICME Congress in Germany last summer. And this poster that I have here with our past math contest was a perfect fit, because at this ICME Congress, then you pick a discussion group and a topic study group, and you stay with that the whole week. And when I found out there was a topic study group on math competitions, I figured that was a good chance to showcase the math contest that I've been involved in for so many years. In this book, the Balkan Mathematical Olympiads, some of those problems are quite complex that I probably would not really be able to use in the math contest. I did find one problem I liked involving prime numbers, and I simplified it to use in the math contest, and a lot of our students got it right.
Okay.
But some of those problems are quite involved, and so I don't think I would necessarily use them. But I was intrigued in terms of seeing what kind of math problems people in other countries might use. So that was of great interest to me to get that book. And I had been to the International Conference on Teaching Statistics in Slovenia in 2010, and at that time I organized a session on people who use sports data in their math classes, which provides a research basis for doing that, because Dean Minkler would like me to develop a math and sports course, so it's good to know that there's a research basis for it. So that caught my attention, that there is a math community of people who are interested in math competitions, and then also that people here in the United States who are interested in best practices and what's going on in other countries. And the other math books on the table, be it from France or Poland, Romania, etc., have different sorts of mathematical applications. The book you're looking at now is in Arabic, which I don't read, but I did go to an international conference on teaching statistics in Morocco in '94. That was my first of several trips to Africa, so that was of interest to do that. So of course the describing language is different, but if they're solving an equation like x plus y equals 10 and other stuff, it's all going to look like the same math.
I was thinking about you the other day, because these are Arabic numerals that we use. So they have that as their root, and it's a base 10, isn't it? A base 10 system.
Yes, our system is base 10.
But everything in the internet world, or the world of IT, is a binary. It's zeros and ones.
Base 2.
And the Mayans had a 5 base. So what do those mean? Why is a binary 0 and 1 maybe more powerful in application in technology than a base 10? There
Yeah.
must be pluses and minuses to each one of these things, not to extend the mathematics metaphor.
That's good.
Yeah.
I like that.
Yeah.
That's good. Yeah, a lot of our students who go into like computers and programming, would use that kind of binary stuff because, see, when you have base 10, you're using the digits 0 through 9. If you're doing base 2, it's 0 and 1. And so the binary seems to be a very valuable system for those who might be in computers and programming. So that's a whole area that, if people are in math, could also go into in terms of computing. I had a calculus class a few years ago where they wanted us to have a math major, and then of course now we have the math pathway. But a lot of the students in that class did go into computers and programming, and so there is a mathematical basis for doing stuff like that. So that's an application also.
Right. But within a binary system, for example, would calculus work? Or is calculus totally in the embrace of a base 10 system?
Well, what we talk about in calculus in terms of functions, rates of change, our listeners might be familiar with ideas like velocity, acceleration, stuff like that. And then when you talk about rates of change, which leads to derivatives and later on to its opposite, integrals, which we do so much in Calc 2, and then infinite series, then you're not really doing a lot of that kind of arithmetic stuff because so much of it involves variables x and y and things of that nature. Now, in terms of people who might be on the STEM track, science, technology, engineering, and math, who might go on in calculus, then, you get into applications that involve the calculus like area, volume, surface area, arc length. And right now we're talking about infinite series, convergence, and divergence, which leads to how could a function be described as a whole infinite string of terms.
Right.
So the arithmetical side doesn't show up in terms of numbers quite as much as they would in earlier classes.
I think I understand. I'm sad to say that our half hour is over, but I really want to thank you for coming to talk about mathematics, and I'm feeling like we just scratched the surface. This is a huge topic. So thank you, Steve Krevisky, for being a perennial guest on my show. Don't forget to watch out for the Cleveland Indians and the Washington Nationals next October or November, just to see if he's right about his prediction. This is Anna Wasescha, president of Middlesex Community College, wishing you all a very good day.